Welcome back to another video. In the previous video, I gave you the properties of divisibility, these 8 properties that you have to know. But today, we are going to look at the extension of this property, which is if A divide B and A divide C, then we can have A divide bx plus cy for every integers x and y. So how can we extend to this corollary? Okay, so let me state this property again. If you have A divide B and A divide C, you're gonna have A divide bx plus cy. So if you have the divisor of A, let's say A divide B, A divide C, A divide D. So you're gonna have A divide bx plus cy plus dz, where x, y, and z are integers. Okay? Or if A divide 4 numbers, you're gonna have A divided by the sum of these 4 numbers. So take a look at this corollary for any integer a, b1, b2, and all the way to bn, such that a is not 0. If a divide b1, a divide b2, all the way to the last one, a divide bn, then a divide b1x1 plus b2x2 all the way to bn xn, where x1, x2, x1, x2, all the way to xn are any integers. For example, you may have, let me think of this, 5 divide 10 and 5 divide 15. What can we write? You may have 5 divide, okay, let me try to write 100 times 2 plus 15 times 3. Okay, can we factorize number 5? Yes, we can, right? So we're gonna have 5 times 10 times 2 plus 5 times 3 times 3 and factorize number 5. So we're gonna have 5 times 10 times 10 times 2 plus 3 times 3. So we factorize number 5. That means that 5 divide this one, right? That means that 5 divide 10 times 2 plus 3 times 3. Okay? That's what we have right here, right? Oh, I think I missed something. Did I miss something here? 5 divide 10, 5 divide 15, and try to write 10 times 2 and oh sorry, this must be 15, okay, not 3. This must be 15 times 3, right? That's what we have. So now take a look at this corollary and we try to prove it. So I want to use a proof by I want to use the principle of mathematical induction. So we have to let A, B1, B2, all the way to B, let me use L, okay? B an integer such that, so I just gotta write just B, okay, B1, B2, all the way to BI, such that A is not 0. For L being 1, 2, 3, and all the way and so on. Okay? Now, I want to write let Pn be this statement. So A divide B1, A divide B2, and all the way to a divide bn, and then a divide b1 x1 plus b2 x2 and plus all the way to bn xn. Okay, where x1 x2 all the way to xn are integer. This is our bn. Okay, this is our bn. Let's take a look at the base step. Okay, what do we have in base step? We use n equals 1, right? So we're gonna have a divide b1. Okay, for a divide b1, what do we have? So we gotta have there exists q1, which is an integer, such that b1 equal a q1, right? Okay, so how do we write bx? Then what is b1x? b1x become a q1 times x, which is a times q1x. That means that a divide b1x, right? So a divide b1x. Okay, oh, I forget to multiply x1. Okay, that's what we have. All right, where x1 is an integer. Okay, this is the base step. Now let's go to inductive step. Okay, let's go to inductive step. So we can assume that pk is true for any positive integer k, and we try to show that pk plus 1 is true. Okay, so what do we have right here when p of k is true? Okay, since pk is true, what do we have? Okay, since pk is true, we gotta have, so what do we have here? We gotta have a divide b1, a divide b2, right? Dot all the way to a divide bk. Okay, and then a divide b1 x1 plus b2 x2 and all the way to bn xn. All right, where x1 x2 all the way to xn are integer. Okay, what can we do with this? I want to show that I want to show that pk plus 1 is true. So I have to assume this. So I have to assume that a divide b1, a divide b2, all the way to a divide bk, a divide bk plus 1. Assume this one and try to write this term. Okay, so what do we have here? So we gotta have, so let me start with this. So we gotta have b1x plus b2x2, okay, plus b3x3 and all the way to bkxk and plus bk plus 1, sorry, bk plus 1 xk plus 1. And what happened to here? this one is already divisible by this term. So I forget to write this one here, right? So I forget to write the divisibility. So there exists q, which is an integer, such that b1x1 plus b2x2 and plus all the way to b. Okay, this should be k, not n. Okay, this should be k. Sorry for my mistake. This is k and k and k. This is b k x k. So this sum turns into be a times q according to divisibility. So what can we do now? So from this right here, I think I have to just assume that a divide k plus 1. Okay, just assume that a divide k plus 1, right? And then there exists q k plus 1, which is an integer, such that bk plus 1 equal to a times k plus 1. Okay, qk plus 1 like this, right? So let's write this term. So we have the sum from b1 to bk. So this must be 1. So we're gonna have, so we focus on the first k terms. Okay, focus on the first k term and plus bk plus 1 x k plus 1. And for the first k terms, we're gonna have aq. Okay, plus this one right here. So what do we have? We substitute this one into bk. So we're gonna have ka qk plus 1 xk plus 1. And factorize a, we're gonna have aq plus qk plus 1 xkq plus 1. So that's what we have right here. So we have shown that a divide this sum, right? A divide this sum. Okay, therefore p of k plus 1 is true. Okay, p of k plus 1 is true. So we have shown that corollary 2.3.2 is true. Okay, so in the next video we will give you the example of these properties, and that's it for this video.